Welcome back, I'm That Chemist, and today we're going to be deciding which inorganic compounds are the most cursed. So for today we're going to be talking about inorganic compounds, and the molecules that go in here have to be somewhat inorganic, and we're going to be ranking molecules based on how cursed they look. So without further ado, let's get started. So this first one here, let's look at this krypton in this C60. So it's actually possible to get metals and other atoms inside of a fullerene, also known as a buckyball. This is called an endohedral fullerene, and endohedral fullerenes are somewhat challenging to synthesize, although people have found methods for their synthesis. Now, I think it's pretty cursed to have atoms inside of another atom. I think fullerenes are normally pretty boring because they don't see too much application for traditional organic chemistry, although this time we have an atom inside of it, and that's pretty awesome. Now, you might not think that this is inorganic, but in my opinion, fullerenes aren't very organic. If you disagree, you can comment down below. As you can see, we have a lot of interesting ones to get into today, so let's get started with another noble gas. So in this case, we have bis perfluorophenylxenon, which is able to be isolated, although it's not that stable. Most of the time, noble gases don't want to form complexes. They don't want to be anything other than a neutral noble gas, although it's possible to do it with some elements like xenon. Here we have krypton in its neutral form, but here we have xenon in its +2 form, with these two aryl ligands. So this one isn't particularly stable still, although it is pretty interesting to have a carbon-xenon-carbon bond. So I think at the very least, this one probably has to go into B tier. Now, for a lot of these, you might wonder, well, what are the applications? And the answer is there isn't. And there's a lot more of that in inorganic chemistry, in my opinion. But when an inorganic reagent is useful, it's extremely useful. So here's an example of that. Grubbs catalyst. If you're not familiar with Grubbs catalyst, it's often used for a reaction called ring-closing metathesis, which is a way to take two double bonds and snap them together to form a big ring with a double bond in it. Additionally, you can use these catalysts for ring opening polymerization, amongst other reactions. So olefin metathesis, the exchange of olefins, is really useful, and Grubbs chemistry contributed to this in a major way. Grubbs passed away somewhat recently, and so I thought it would be appropriate to include a carbon double bond ruthenium complex in this episode. So double bond carbons to metals are relatively common. They're not super duper common, but they definitely do exist. So I think for that reason, we'll put it in C tier, but because we're only considering how cursed it is. So it's not too cursed, but it is extremely useful. Now, a very cursed one is this one here. So I've called this one Schrobelgen Special because they didn't have a name for this compound in their paper. But what Gary Schrobelgen and his group did is they made this compound with two different noble gases in the same molecule. So they were able to isolate this as the hexafluoroarsenate salt, and you can see this is just kind of crazy. They've got a krypton right next to a xenon, which is kind of interesting. So I think two noble gases in one molecule, in one complex, definitely goes into S tier. Plus it's for Schrobelgen, so that's appropriate. Now another interesting one is this helium hydride. And the interesting thing about helium hydride is it can be isolated in a laboratory, although it's extremely unstable. Now the most noteworthy thing about helium hydride is it's believed to be the first molecule that ever came into existence shortly after the Big Bang. So this is kind of an interesting molecule. It's definitely cursed because we have helium, the smallest noble gas, with something else connected to it, which is extremely challenging to do. So I think helium hydride also has to go automatically into S tier. Now let's look at some other ones. So here we have boron triazide. And so boron triazide is like less cursed, I would say, compared to some of the other ones. You know, when you're comparing a boron connected to an azide, and then you compare that to like, you know, two noble gases together, it's pretty obvious why this isn't going to go into S tier. You know, it's still kind of cool. It's got a lot of nitrogen content to it. It's not super sensitive on its own, but when complexes of it are made, it becomes more sensitive. So this is a high energy compound, an energetic compound, and because it starts with a B, we'll put it into B tier. Now we have this other one here, manganese heptoxide. So those manganeses are super duper oxidized, right? They're already in a +7 state. They don't really want to be sharing that one oxygen, and for that reason, manganese heptoxide will oxidize almost anything, including hexane or cyclohexane. I've actually even had success oxidizing polypropylene with it, and it blew a hole into a polypropylene Eppendorf. Additionally, when this decomposes photochemically or thermally, it makes ozone, and so this is extremely cursed. We're going to put it into A tier. Now, we have a lot of ones here that are fairly cursed, so we can rearrange some of these later on if it gets a little bit competitive. So here we have a really interesting one, this Einsteinium complex. So this is actually the first complex of Einsteinium that was ever prepared. You can see this is a big bulky metal. It's definitely interesting to see this polydentate ligand. Polydentate just means there's a lot of different parts of the ligand, which is the like binding molecule that complexes a metal. Polydentate just means it connects from many different positions. So if you had like bidentate, that would mean it's connected two different ways, like from two heteroatoms, for instance. But in this case, it's polydentate because it has so many. This is so big that I don't think we can just put it into one tier. It's definitely kind of cool, although it's not as cool as some of the other ones in here. If you make a big enough ligand, it'll wrap around anything, so we'll put it between E tier and F tier. Now, another interesting one here is this potassium octachlorodimolybdate. And so here we have a molybdenum-molybdenum quadruple bond. And quadruple and quintuple bonds are extremely uncommon in chemistry, although they can sometimes be done with metals with big enough shells. So the orbitals that form these need to be sufficiently large. So you can't do this with things like carbon because they're much smaller orbitals. So a quadruple bond is a little bit cursed. So I think we're probably going to put this one in C tier. Although there's some other really cool ones that we need to get to. One such example is diphosphorus, a phosphorus triple bond phosphorus. Now, if this was nitrogen, that wouldn't be too exciting for you, because it's just like nitrogen gas, we have it all the time. But to get phosphorus to behave the way nitrogen does takes quite a bit of work. So this is usually generated in situ, and then it can be trapped out to make diphosphonines through Diels-Alder type reactions. So this one's pretty cool. It's also unstable, so that's kind of gives it a little bit more street cred. But, you know, compared to some of the other ones, it's just a little bit less cool. It is a phosphorus triple bond phosphorus, though, so I think we can put it at least in C tier. The next one I want to talk about is Teflic acid. So Teflic acid is a very strong acid, and once it's deprotonated, it forms Teflate salts. And Teflates are some of the least nucleophilic anions that exist. So this can be really good if you're preparing transition metal complexes, for instance, and let's say your ligands keep doing stuff and your counter ions interacting with your molecule or your complex. It can be advantageous to use a Teflate in those cases. Although there's not too many groups that have used these, they have promising characteristics for future inorganic chemistry. So Teflic acid doesn't look that cursed. It just kind of looks like, you know, every metal and their dog. You can put a bunch of fluorides or an OH on it. So we're going to put it into F tier, which is appropriate because there's plenty of fluorines on it. Now this interesting one here is argon fluorohydride. You might be thinking, wait, argon can form compounds? And sure enough, it can at 8 degrees Kelvin in the presence of a laser on a cesium iodide surface. So those are pretty specific conditions to get argon fluorohydride, although they technically exist. So this has been characterized by IR, so it does exist. Although most of the time it doesn't want to exist. I would say this is also right into S tier because that is super duper cursed. One that I'm a really big fan of is hexaferrocenylbenzene. So here you can see they've got 6 ferrocenes coming off of a benzene. Now you might be wondering, what's this used for? And again, like I said earlier, a lot of the time in inorganic chemistry, the answer is because. Okay, so this is pretty cool looking, but again, it's also pretty massive. So because it doesn't have any characteristics, we're going to have to, or any useful properties, we're going to be a little bit more harsh on it, although it does look pretty cursed because look at how floppy those things are going to be. They're going to be sticking all over the place. I'm actually quite impressed that this could be synthesized because hexa-substituted benzenes are challenging to make at the best of times. So I'm going to put it between C tier and D tier. Now, everybody's favorite we have right here, FOOF, dioxygen difluoride. And it's often joked that the reason it's called FOOF is for the sound it makes because it's highly explosive. And it turns out that this actually does have one application, which is in the synthesis of plutonium hexafluoride, at least by one laboratory. So quite an interesting molecule, definitely cursed because fluorine absolutely hates being anything other than fluoride. We're going to have to put this right into S tier. Now, similar to some of the other noble gas compounds, here we have radon difluoride. Now, radon's below xenon. It's typically you think of radon as something that people in basements get poisoned with if they don't have proper ventilation. So radon difluoride, it's an interesting compound. It's still pretty cursed because it's a noble gas with 2 fluorines. But, I mean, if you compare radon difluoride to helium hydride, it doesn't even compete. Not even close. So for that reason, I'm going to put it into D tier. The further down you get, the easier it is to make compounds from those, generally speaking. So I'm a little bit less impressed with radon difluoride, although I wasn't familiar with any radon compounds before working on this episode. So here's another interesting one, perzenic acid. So it turns out that you can oxidize xenon quite a bit. So here we have perzenic acid. This is not a particularly stable compound. It can be prepared from xenon trioxide, which is prepared from xenon hexafluoride accordingly. And yeah, you could oxidize xenon several times, but it's going to do whatever it can to go back to elemental xenon if possible. So it's not super stable, and it looks pretty cursed. So I think we can put it in B tier. Now, chromoesters. You might not have heard of chromoesters before, but the reason I came across these was I wanted to make selenonoesters at one point. And you might be thinking, wait a second, don't you mean selenoesters? And for nomenclature's sake, I would prefer to say selenono, like thiono, where it's clear that I'm talking about the carbon double bond selenium or whatever the chalcogen is. So if you have an ester, you have a carbon double bond oxygen. If you have a thionoester, you have a carbon double bond sulfur. And if you have a selenonoester, you have a carbon double bond selenium, okay? And so this is like similar to carbonyls, and in fact, you can even call them these things apparently. And these can be useful intermediates for preparing thionoesters and selenonoesters. So this is pretty cursed in my opinion because it's got carbon monoxides on it. It's also got a chromium double bond carbon. So I'd say this is pretty cursed. It's at least going to have to go into C tier. Now, Arsenicin A, this is actually a naturally occurring compound. This is present in some marine sponges, and it's pretty toxic. It's not a great compound. It's a little bit cursed because it has arsenic in it, but all those bonds look relatively stable. I think we're going to have to be a little bit more harsh and put this into E tier. So we have this interesting palladium dimer complex. And so sometimes when you're working with transition metals, you can form transition metal bonds. And so here we have a palladium-palladium single bond. Additionally, it's worth noting that each of these palladiums are palladium-1 species, which is pretty uncommon for palladium. You typically think of palladium-0, palladium-2, palladium-4, but in this case we have a palladium-1 dimer species. And this has been used by the Schoenbeck group for cross-coupling chemistry. So I think seeing the bridging iodide ligands too is also a little bit cursed, so it's not like one of them just has all the negative charge given to it. They're actually sharing both of the iodides. And some similar compounds have been prepared with trifluoromethylthiolate as well as bromide derivatives. So definitely a more interesting compound. Not too cursed, but definitely interesting. So we can put it into D tier. Now here we have this thiomolybdic acid. So thiomolybdic acid is used for the treatment of Wilson's disease, which is a rare disease where the body accumulates too much copper and you can't get rid of it fast enough. And so the reason it works so well is this just forms a really stable complex with copper, and it helps clear copper from the body. It's also been examined for some use in cancer treatment. So definitely an interesting compound. Not too cursed, but it does have 4 sulfurs on it. So, I'm tempted to put it in S tier. But, we're trying to be as straight line as possible here and really put the noteworthy compounds in S tier. So I'm going to put it in B tier. Now here's an interesting one, dinitrogen pentoxide. So dinitrogen pentoxide is just dehydrated nitric acid. It's pretty good as an oxidizer. As you can see, there's a lot of oxygens in there. It can be used potentially for rocket fuel, although it's a really potent one. So let's say probably A tier or B tier. I mean, let's put it in B tier. Again, if we're comparing it with a noble gas inside of a fullerene, that's pretty lame in comparison. So we'll put it in B tier. Now, another interesting one that you might disagree with is tetraphosphorus dicoxide, aka P2O5. In this case, it forms a tetramer. Most of the time it's a tetramer, but it's easier to just say P2O5 because that's like its empirical formula. So P2O5, useful as a dehydrating agent. If you need to like get rid of an equivalent of water in reaction, you could use P2O5 sometimes. So for instance, like if you wanted to make dinitrogen pentoxide, you could do that with P2O5. Now it's not that cursed, but all those phosphoruses are really unhappy that they don't have water connected to them. So this will react with water very vigorously. Not super duper cursed, so we'll put it into F tier. Okay, so another interesting one is ammonium dinitramide. So this can be used as a potential oxidizer for rocket fuel. I don't think it's seen too much actual use, although it is a promising compound. It's definitely cool to see 3 nitrogens in a row and not be an azide. And so I think for that reason, we're going to have to put it into S tier. This is like an oxidized azide, which is a little bit terrifying. Now here's an interesting one, Cacodyl. Cacodyl is an interesting compound, and it's found in something known as Cadet's fuming liquid. So it's definitely toxic because it produces, volatile arsenic derivatives. It's prepared using arsenic trioxide as well as acetic acid. So this compound's somewhat cursed. We can put it into A tier because it has an arsenic-arsenic bond, which is like an analog of hydrazine, and that's pretty terrifying. Now, one of the coolest ones on here has to be this tetraxenon gold species. So this tetraxenon gold species has been prepared using gold trifluoride, as well as xenon in the presence of HF. Super duper crazy looking compound. I think this one definitely has to go in S tier because it's both got gold and xenon, 2 elements that we typically think of as noble, being like wanting to be neutral. Although in this case we have the xenon partially positive and the gold partially negative. Just the net charge will still be positive, so it's really like the gold has the positive charge, but nonetheless, it's something that can be prepared in equilibrium with other species. So an interesting compound nonetheless. Another interesting one is dicobalt octacarbonyl. So dicobalt octacarbonyl can be useful for the activation of alkynes, amongst other things. You occasionally see it used, but oftentimes it can be challenging to remove the cobalt from the alkyne if you're using it as like a quote-unquote protecting group. So this has a cobalt-cobalt bond. I think that's pretty cool. I also like that it's really hard to look at this and know what you're talking about because there's carbon monoxide connected to the cobalt. And so you just see CO, CO, and it's like, okay, it's a little bit overwhelming to look at. So a little bit cursed. I think we can put it into C tier. I mean, there's a lot of C's in that molecule, so I think that's relatively fair. Now, another interesting one is Borazine. And again, you might be wondering, how useful is Borazine? And the answer is, well, it depends. You can make boron nitride with it, but it seems like there's a lot of other ways to make that, although some inorganic chemists have looked at chemistry of this. I don't think Borazine is that cursed because it just looks like boron mixed with, ammonia. It's not too cool. I think we could be a little bit rougher on that and put that into E tier. Now, we have a couple interesting ones left. We have Uranocene, we have Rhodium acetate, we have Diborane, and we have Lewisite. So the last one we have is also C2N14. C2N14 we briefly talked about in a previous episode with Tom from Explosions in Fire. If you haven't checked out that episode, I'd encourage you to do so right now. And this compound is very energetic. I don't think it's seen any actual application because it's only been prepared in a relatively small scale, although you look at that and there's a lot of nitrogens in a row there. It's definitely an appealing looking molecule, and I think we're going to have to put it right into A tier. And since it's got so many azo groups, I think that's appropriate. Now, Diborane. Diborane is really interesting because it's usually the first example used to teach students that ligands can sometimes bridge two molecules. So in this case, we have like one atom, a hydride, that bridges both borons. It doesn't have to just be bound to one thing. Even something like hydrogen with the 2 electrons it has can be bridged between 2 molecules, and so that's a little bit interesting. Now, Diborane has a lot of synthetic applications, and when you compare it to the other ones, I just don't think it's quite that cursed, but we can put it into B tier because having the hydride shared between 2 borons is still a little bit cursed. Now, Uranocene is a uranium sandwich. I think any chemistry with uranium is inherently interesting because it's got uranium in it, and most of us would be too afraid to work with that. And in this case, I think it's the most studied 8-pi system for sandwich complexes. So it's pretty cool looking. I think Uranocene can go into B tier because it's a little bit, or no, let's be more harsh. We can put it into D tier because there's plenty of sandwich complexes that exist, and this is just a bigger one. Now, that being said, it is an actinide, so that's kind of cool. Seeing an actinide sandwich complex, definitely pretty sweet. So we have 2 left. We have Lewisite. Lewisite is actually a chemical warfare agent. It's something not super duper friendly. It's used as a blistering agent. It's definitely a terrible compound, and for that reason it's cursed on its own, but because we're looking at like structural cursedness, I think we could be like a little bit harsher on it. It's got chloride in 2 different contexts, both as an arsenic chlorine bond, which is scary to me, but it also has like a vinyl chloride. So this one's a little bit more organic, so I don't think we can count this one too high, and because it's F'd a lot of people up, we can put it into F tier. Now, last but not least, we have rhodium 2 acetate. Now, I kind of don't like rhodium 2 acetate. It has a rhodium-rhodium triple bond, which is kind of cursed, but I think it's overused in synthesis. I think people take a lot of diazo groups and they make their carbines using rhodium acetate, but rhodium's a little bit expensive. So it's definitely useful. It's a useful way to generate carbines. You often see a little bit unimpressive chemistry done with it, but nonetheless, it's got a rhodium-rhodium triple bond. I think that's kind of cool, and so I can put that into A tier. So hopefully you've enjoyed this tier list. I'd encourage you to leave a like and subscribe, and check out some other videos from the channel. I hope you have a great day. I often think back at how we figured out which one was delicious, which one made someone sick, which one killed you, and which one made you see God for a week.